Hi, I'm going to present about our Assignment 3 Data Analytics for Semester A 222. This is our group members, which is Soleh, numeric 289509, Syafiq 289869, and me, Suchira 288316. Our objective for this assignment is to develop a prediction model that analyzes its performance. Our dataset is contained about 10 years of daily weather observation from many locations across Australia with 23 features and 145,460 records. Then our target variable is rain tomorrow. Our source of dataset is from Kaggle. So our features of dataset will be date, location, minimum temperature, maximum temperature, rainfall, evaporation, sunshine, the direction of strongest wind gust in the 24 hours to midnight, the speed of strongest wind in 24 hours to midnight, and the direction of wind speed, wind humidity, atmospheric pressure, and also cloud at 9 and 3 p.m. and lastly with the temperature at 9 and 3 p.m. Rain today, rain tomorrow. Then our dataset problem is to predict next day rain. The hypothetical solution is by tree classification model on the target variable, which is rain tomorrow.
Hi, I'm Soleh Majid, metric number 289509, and now I will be explaining on the machine learning algorithm that we have used for this assignment. The machine learning algorithm that we have used is the logistic regression. So how it works is that it is a supervised learning algorithm and it is suitable for binary classification and predicts the probability of the rain. The principle is such as the map features the probability using logistic function and calculates the combination of features and weight and finally learns the optimal weights during the training. So the characteristic of logistic regression is such that it has a binary classification capability where the effectiveness for analyzing binary outcomes such as predicting yes or no scenarios and also useful in various real-world applications where decisions are binary. It also has feature importance analysis where the coefficients indicate the importance of features in the algorithm, also guiding feature selection, and finally dimensionality reduction. It enables data analysts to focus on relevant variables for deeper insights that they want to gain from the dataset, which leads to the strength of this machine learning algorithm, such as the quick and efficient model training. It requires only minimal computational resources, making it suitable for large-scale data analytics tasks. We have a dataset of thousands and thousands of rows, and it enables faster model development and iteration to process the dataset that we have put on. It also is good at handling missing data, such as the robustness to handle missing values in the dataset without significant data pre-processing efforts. It reduces the burden of data imputation and data cleaning tasks. Hence, logistic regression aligns with our problem and data requirement. We have seen that the binary classification capability of the logistic regression aligns with the problem, which is to predict the next day rain, which naturally a binary classification problem where we have the output 1 to 0 that indicates yes or no, whether it will rain or not, based on the weather features available in the dataset. And we can also identify linear relationships. The logistic regression is effective in capturing this relationship between the weather features and the likelihood of raining. If certain weather conditions, let's say for example high humidity or low pressure during the day, it has a linear impact or rain prediction. And we can validate this with the logistic regression since it is good in detecting and model such a relationship.
Now for model development, after cleaning the data, we split the dataset into 9 main folds and one experimental fold using the code on the screen right now. The folds are 1090, 2080, 3070, 4060, 5050, 6040, 7030, 8020, and 9010. Now the experimental fold, however, we did 0.01 to 99.99. Now, to evaluate our model, we'll be using 5 different evaluation metrics, starting off with accuracy. Accuracy is how often a model is correct, measuring the ratio of correct prediction to the total number of predictions. In other words, can be seen by its formula, number of correct predictions divided by total number of predictions. Now, precision, on the other hand, is how many of the positive predictions are actually correct. The second evaluation metric measures the proportion of true positive predictions out of all the positive predictions, which can be seen by its formula, true positive divided by true positive plus false positives. Now, the third evaluation matrix is recall. Recall measures how many of the actual positive instances are correctly identified. This can be seen from its formula, which calculates the proportion of true positive predictions out of all actual positive instances, given true positive divided by true positive plus false negatives. Fourth is we have error rate. Error rate is the proportion of misclassified instances, including both false positives and false negatives, out of the total number of instances. This means that error rate is actually the inverse of accuracy, given by its other formula, 1 minus accuracy. And finally, we have F1 score, or F1 measure, which combines the precision and recall into a single score. This provides a balanced evaluation by considering both false positives and false negatives. From running all of the different split ratios using our model of choice logistic regression, it seems that split ratio 80/20 produced the best overall results out of the main 9 split ratios. It received the highest precision, recall, and F1 score at 70.51, 43.72, and 54.05, respectively. However, the highest accuracy and error rate score belongs to split 60/40 with the score of 84.52 and 15.47. However, after quite generous discussion, we believe that split ratio 80/20 is the best overall result split ratio that we can get. This is because the accuracy and error rate does not go too far off from the winning split ratio of 60/40 with only a little bit of variation. Moreover, recall score for split 80/20 achieved 43.72, which is much, much higher than any other competitors here. Now, to actually properly evaluate everything, after getting our best fold, which is 80/20, we actually have to see every accuracy, precision, recall, error rate, and F1 measures value and really interpret what that means. Now, for accuracy, we obtain a 84.45% accuracy, which just means that this model can accurately predict 84.45% of the time whether or not it will rain. Although this is quite a high number, this does not tell the whole story. Now, looking at precision, we only have 70.51%, which means that from here we can understand that this model will only correctly predict that it will rain 70.51% of the time, which is not so bad. However, as our dataset is about rain prediction, so having around 30% of false positives wouldn't bring too much harm. This means that around 30% this model will predict that it will rain. However, it is actually just a sunny day, which is much better than what we're going to be talking about after this, which is recall. However, now recall, we obtain a 43.72%, which is less than 50%, which is quite bad. However, this this means that our prediction only predicts rainfall correctly 43.72% of the time. This would mean dire consequences as if it was to predict that to be as if it was to predict that it would be a sunny day, it would actually rain. Meaning that 43 points meaning that the remaining percentage would mean that it will be a false negative, meaning that it will predict that it will be sunny, but then it actually rains. So let's say people were to plan to go on a vacation, go to the beach, hang clothes, have outdoor activities, have a wedding outdoors, and because you trust this model, it might let you down, as it most likely 50% of the time will give you a false negative, which is quite bad. Now, error rate, on the other hand, is only 15.52, which is quite the inverse of accuracy, which means that this model will predict incorrectly around 15.52% of the time, which is pretty fine. However, rain is a chaotic in nature, so it is quite hard to predict. Now, lastly, the F1 measure at 54.05%. As seen before, the F1 measure is the highest, which means that this, out of all the other folds, gives the best balance in getting the best prediction possible for tomorrow's weather. So, although recall is quite low, it is also the highest out of all the other folds. And this might be one of the limitations that we have for this specific model. Insights, limitations, and challenges. Now, although we see a slight decreasing trend in all of the evaluation metrics used, we found out that the evaluation metrics do not vary much as the training and testing ratio were adjusted, specifically as we decreased the training size down to even 10%. Now, this could be caused by the large number of records at 145,460 different records. Now, the problem is when we split it between 1090, where 10 is the training set and 90 is the testing set, we realize that 10% of the total amount of record is still 14,546. Now, this is still a very large number of records, which might even be much bigger than some of the total data sets out there. So, what we feel like could happen was, although the training size was still small at 10%, the number is still big enough for the algorithm and model to learn enough to get a pretty decent and quite accurate score throughout. However, to see if training size does matter, we did do a slight experimental one where we had the training size of 0.0001, or in other words, 0.01%, which would bring it down to 14.546 records for training. So that's around 15 records only. By doing this, we did see a significant drop in accuracy, precision, especially recall, error rate, and which is most important, F1 score. So training size does matter. However, if your dataset is big enough, having a small training size might not be such a problem, as 10% of something big might still be pretty big. And that's all for today. I hope you enjoyed this video, and I hope it was quite informative. Thank you very much from our team.